Welcome everyone to the autumn class of Big Data Analytics. So welcome. I understand you guys would be what? This year, year 2, year 3, first sophomore? Yeah, year 3. Okay, very good. So first of all, just a little bit of ground rule. You guys just come in and then we'll have the name tag here, and again, sit spread out as far as you can. We don't have a big room, but we should be able to keep some decent distance between ourselves. This being Thailand, so we don't have to shake hands. We can sawatdee. You know how to do that, right? So that's very gracious way of doing hello from 2-3 meters. Good. Now, okay. Today is class 1. We have altogether 15 classes. To sort of like a workshop kind of thing, okay, which is very good way, very practical way of learning. But let's start this class by going through the syllabus. Let me go through the syllabus. This guy. Whoops. Okay, let's go to this. Okay. Now, what I want seems to be a little bit of echo. Not sure how to get rid of echo. Do I still echo or is it good now? Good now, right? Okay. Right. So let's. I think เขาต้องปิดซูมไม่ได้เปิดหรือเสียงมาจากไหนวะปิดไมค์นี่เหรอ go figure out. Okay. Right. So, okay, let's get going. So this course really is in a way is introduction to data analytics. จะต้องปิดเสียงปิดแต่เครื่องหนึ่งไหมปิดแต่คอมข้างล่างขวาไม่ใช่สิต้องปิดอ๋อหรือว่าพี่ต้องปิดอันนี้ปิดลำโพงไหนปิดลำโพงคอม Okay, how about this? Is it better? Okay, so we've just wasted. That's all right. 10 minutes.
You can maybe print device when download the device.
Yeah. I think I have to change it to maybe this guy or something. Is that better? ได้ไหมครับตอนนี้ได้ไหมได้ไหมหรือกล้องอีกแล้วป่ะถ้ากล้องปิดเลยดีกว่าอย่างนี้ได้ไหมครับก๊อปโอเคลูกห่างๆกันหน่อยค่ะหนู3 คนห่างๆกัน Okay. Before we get started, just to lay some ground rule, I want everybody to be punctual. It's very easy to be punctual because everybody's got to watch. and everybody is globally synchronized, right? There's no reason to be late. I have a daughter, so I would tell my daughter never date anybody who can't be true to time, because being true to time is the easiest thing you can be true to, right? Because you know exactly when the next minute is going to be. And also, let me share this. This is really interesting. I like to read a lot of philosophy and political science as well. There was a very good piece of writing about the Africa continent. Let's talk about partial westernization. Say one of the mental block was they like to adopt part of the Western value, but not the whole set. And that's become very problemsome. For example, they like good Swiss watch, but they don't like to keep time. So it becomes a decoration, pure decoration, right? So my point is, you don't need to wear Rolex now, because any cheap digital watch will keep you on time. So there'll be no excuse for showing up late. Yeah. So that's ground rule number one. Number two is again, you have to respect the distance. We'll try as much as you can. We'll try to make do. Last year, we actually had to do everything by Zoom. Turns out to be not so much fun for both teacher and students. Okay, so in order to keep this workable, we have to cooperate. So always wear a tight mask. I'm the only one in this room who's not wearing anything, right? And also there's a gel bottle there. Okay. Okay, by show of hands, just start by, are all of you in the applied digital intelligence track, or are you choosing other specialization? Raise your hand if you are choosing the applied digital intelligence. No? No? You from sustainability track? Healthcare? What? Where are you guys from? Oh, so you're not part of Basai? We're part of the Basai. You don't have the track. What about the people behind you guys? What tracks are you guys in? Are you Thai students? No? Oh, okay. So who's actually Basai student who has to choose a track? I'm just curious. Raise your hand. Yeah, what is it? You haven't chosen. Okay, that's all right. Just to give a word on how the Basai program is designed. Of course, it has the 4 tracks, right? It has the applied digital intelligence. It has the sustainability challenges. It has the healthcare, self-service system, and the smart city and inclusive community. The last 3 can be considered problem tracks. In other words, you study the problem and then you look for solution. Applied digital intelligence is the other way around. You study the solution and then you look for problem. Okay, but either way, มันยังนั่นอยู่ ต้องปิดของจอนี้ใช่ไหม Okay, well, let's figure out. I'll go on. Okay, so this is a foundation course. Why is it a foundation course? Because it doesn't matter which concentration you're in. The world is now driven by data. Okay, the world is now driven by data. So analysis of data is going to be ubiquitous with every application. Okay. The first class is always a little bit wasteful. Hello. Are you there? Okay, now we are good. We are good. Start the clock. ก็เรียกมาก็ได้แต่ว่าเมื่อกี้มันลองไม่ดี Okay, finally, let's start again. Welcome to the autumn class of 2002 in Big Data Analytics. Right. First thing we have to understand is what is this class designed for, okay? It's designed to cover data analytics. Okay? The word big is there, and I'll show you why it's a little bit of a misnomer. Okay, it's a little bit of misnomer. When we go into the terminology, you understand why this class is really data analytics, and you should put like the big in the bracket. Okay, so this class is designed to introduce you to how a professional data scientist, say, such as myself, in whatever area of application, would look to using computational tools and devices and mathematics, applied mathematics, probability theory, statistical inference, and of course, the latest in machine learning technologies to basically give us a good handle on what the data is telling us. Okay? The data in itself is supposed to be an evidence of phenomena in the real world. It doesn't matter what it is, okay? We take it for granted that whatever happens in this world, it gets recorded as data. Now, this didn't used to be the case. It used to be where you can walk around the street, but until you write something down in a journal, it doesn't get recorded. Okay, the world has changed. Now, just by you walking down the street, you are generating data. Okay, and that's what I mean by data analytics has become sort of like the cornerstone of every specialization. So even if you're going to study healthcare, there's going to be a lot of data analysis aspect to that. Yeah, I hope that doesn't bother you. It bothers me a little bit that this microphone is feeding into that, but let's keep going. Okay, the objective is 3-4-4 actually. First thing first, it's supposed to, in a classroom setting, put you in the mindset of what a real data scientist would do when faced with a problem. Okay, so it's going to be like a little bit of a mock exercise here and there. It's going to be sort of like giving you the taste of what it's like for me personally, as a professional data scientist or researcher or consultant. When we face a project, we face a problem, how do we prototype or develop solution and then prototype the application that would summarize the technical tools we use to solve a particular problem. Okay. The second objective is we don't want you to be an uneducated user of machine learning, statistical tools. We want you to be able to look under the hood and understand how and why it works. Now, understanding how machine learning models work, how data analytics tools work, doesn't mean that you will actually be in the driving seat of, writing the actual codes to develop a new algorithm. Not that level. But the code you are you're going to be writing codes, but at the level of a sort of like a middle level user. So you use like a software, or you use a program, or you use a library that some, researcher has already built, given and put that in some kind of algorithm library. But that algorithm is just a tool, and then you have the problem over here. They don't meet. Okay, you have to program the bridge. It's kind of echoing. If you can turn off the speaker here. Apparently there's a speaker that comes with the television or this thing here. So if you can turn off the speaker here, then there will be an echo. Okay, does that work? Batman? Okay. I just turn that speaker off.
Hang on.
Okay. Wow.
เดี๋ยวนะ แต่ว่ามีภาพสวย
Hello, hello. Does it still echo? Does it still echo just a little bit, right? Yeah, it's bearable. Jessica, what I mean is turn off the speaker of this one, not the Zoom. What's on the Zoom program? Just turn off the speaker. Yeah, the Zoom, I mute the Zoom already, but apparently it's picking up. Okay,ครับ. Okay, so where were we? All right. There are, I'm just going to use my voice for now, okay? And that's right. There's a very strong temptation nowadays because of all these tools in data science and ready-made applications. There's a very strong temptation to just say, I don't have to know anything about how machine learning algorithms work, right? Just take it and then put some data to it and then get the result, okay? That's a little bit like, I don't care how the car drives, okay? So I just want to drive from here to there. I don't need to know anything under the hood. Sometimes that makes sense. But a lot of time, it's not that simple because the journey is not predefined. So if the journey is not predefined, you have to understand the limitation of the transportation mode you have. So you just can't say, I want to go from here to there, I'm going to drive. Okay? If that's already been done, that's like a homework. That's like a simple thing. Nobody is going to pay you. You're not going to get any value out of doing that. That's just a baby exercise. A real journey, whether it's in business, in data science, and so forth, is going to involve some kind of new territory, right? And new territory doesn't mean you can drive the same car with the same set of cars. There's a limitation, there's a tool. Sometimes you say, well, from this length of the travel, it's better to go on a motorcycle. Okay, so if just to choose the right mode or the right tool, you have to understand the tool to understand the limitation. That's the name of it. So the objective of this class is for you to not be a blind user of data science tools. And there's a lot of temptation, and you go to industry or trade show, you always have some salesman come and say, oh, this is the perfect machine learning AI tool that requires you to know nothing about anything and just show the data to it, and then you get some result and you can make money. If it was that simple, the problem would have been solved. Your competitors would have already made money from that problem. Okay, so you have to understand the mathematical, statistical, computational foundation underneath. That's the second objective. Third, get some experience coding. Okay, not because you're going to be a coder, but even if you end up being, say, CEO of a company, you have to be able to communicate to the technologically inclined aspect of your organization. Yeah. It's really funny, but you get a lot of respect from your tech guy if you speak their language. You get no respect if you demand your tech guy to speak your language, right? So a tech guy comes in the room, okay? Now, by right, you have the right to say, translate the technical stuff into simple stuff that I can understand. As a boss, you know this, okay? But you never get respect from that. If you actually go down and speak on the technical language with them, even if you are, a very naive or novice technologist, you get a lot more respect. And you think, and they will try to translate that technical stuff to your trade. Okay? And now I found that to be very true in practice. Finally, because this class is going to have some kind of project, it's going to allow you to work in what's called agile development environment. What it is I'll just give you one sentence or two on it. It used to be where a company needs some software to do certain things. And they'll have a committee that have a theory committee, draft out the objective of the exercise, write out all the specifications, make it so watertight, and then contract some consultant or IT developer and say, okay, this is what I want you to do for us. And the timeline is 8 months. See you. And then 8 months come in, and that's the IT or whatever consultant delivers the project. Usually that fails. For one thing, you can never anticipate all the nitty-gritty aspects, all the subtle nuance of the problem. Number two, communication is not perfect. And the perfect form of communication is basically mathematics. Then you cannot go wrong. But most of the time in the project, you specify what you want something to do, and use in English or Thai or whatever language, even if it's embedded in legal jargon and all that, it's simply design. Okay. So what's agile working environment is like in the project, you get the clients, people who want to use the stuff, and the developers, people who are building the stuff together in a team. Okay? And they work on a prototype mode. They try the solution, see if it works, and they keep adding complexity. So they started something that completely failed the mission. Okay, you want to do here to there, and you start with something that achieves something from here to here, or from here to there, but for very limited cases. And then you see if it works as a proof of concept, and you start to embellish degree of realism or generalization into the project. And as you go on, it works better because there's no surprise. It's not like in 6 months' time, you give me something I can't use. It's more like you understand along the way how the problem definition changes. And it sounds a little bit like you're trying to sneak a way of compromising the problem. But sometimes that's not the idea. You're not making the problem easier as you go along, but you actually redefining the problem to be more realistic. Sometimes you actually become more ambitious. Okay? And it's a way of discovering what the data is allowing you to do. So those are the 4 objectives. Okay. So sort of like put you in the mind of a data scientist, even if in a very contrived artificial classroom setting, right? Get you to understand the underlying mathematics, the underlying theory, so you will understand the assumption that goes into a particular technique, particular algorithm. You will see that assumption is a little bit like indication on the medicine. Sometimes you can't, the drug is good, but you can't use this for this person because he's got diabetes. Okay, this is the kind of thing that you need to know the underlying foundation of the mathematics and the algorithm. And again, the third objective is for you to have some experience coding, and the 4th objective is for you to have experience working in an agile environment. Now, for that, we might form groups. Yeah, it might be some kind of group project. Okay, so let's do that. ไม่สำเร็จใช่ไหม Okay. Right. So let's go to now. I tend to not like to use slides very much. You know, PowerPoint slides. But you should. You know why? PowerPoint is very good for sales pitch because it linearizes the narrative. Okay, so I have got you on a captive audience today. You got this problem, slide number 2. The problem is big, slide number 3. If you solve this problem, you're going to make a lot of money. Slide number 4, there are so many solutions. Slide number 5, my solution is best. Slide number 6, pay me. That sort of thing. Yeah. I don't really favor it as a teaching tool. Yeah. It's a very easy thing to use, but it's not even as good as a blackboard in the old fashioned because it's more interactive. You can actually steer the content of the class to them. But what I do use is what's called a mind map. That mind map is freely available everywhere. I happen to use Xmind, so you guys ought to download that, Xmind, and you can read the Xmind that's a mind map that I give you. Okay, so there are 3 elements to this class. Okay. Data analyst and data analysis as a whole, because that's the whole subject. And then the tools. Now, the tools I put here as 2 groups, 2 little blocks, statistical method and machine learning based. Okay. Now, you will have the option to take, you know, follow-up class in machine learning and so forth. Likewise, I assume that in year 1 or in high school or whatever, you have taken probability and statistics course. Okay, so I'm not going to spend so much time in the statistical method thing. Chances are, for whatever problem we're looking at, I will be using machine learning family of tools. Okay, but let's not jump ahead of ourselves. Let's go to 3 things. What do you mean by data? Yeah, let's stop. Well, let's go one at a time. Definition. Well, data is always a resultant of something, some kind of measurement or some kind of report. Okay, I mentioned to you before that in the old days, you only get data if somebody deliberately records something. You know, like Sumerian, they record the grains that they have in the harvest with a little cuneiform. Okay, well, you can do that with Excel, you can do that with data, but now you can actually generate data as you go along. So the essence is not whether or not you do deliberately generating the data or you are volunteering the data. In fact, you know, this privacy issue is all about you becoming the data without wanting to be the data. So the key element, the key aspect of what makes a data is that it's a measurement, it's a record of some kind. Okay. And roughly speaking, it's a record that pertains to some kind of entity, some sample of entity. Okay. Sample of entity. And notice the word sample, that's already that should already take you back to the statistical class, right? You don't know about the whole population. You don't know the height of every single person on Earth, but you know the height of a statistical sample of, say, male Thai person. Okay, so it's always something that pertains to sample entities. It's not usually not the whole deal. Okay, or some kind of series of events. And right away, this should harks back to some of you have taken this like time series statistics. I don't know if you've done that. Okay, well, think of gasoline price. Gasoline price is kind of random variable. In other words, for a given day, you don't know what it is. Yeah, so you don't know what the price of gasoline will be. But it's not only you don't know what the price of gasoline would be. Once you knew, that knowledge is only limited to that one day. Tomorrow you don't know again. So that same thing is not just one randomness, it's every randomness. Every time you want to know the price of oil today or price of gasoline today, you don't know tomorrow. Yeah, but you know the past. Just like I can take a sample of height of a sample and infer on what the height would be for the rest of the population. Time series is a little bit like sampling from the past to infer about the future. Okay, so it's a different set of sampling. Okay, the first set of sampling is you have, whatever, 60 million Thai people, you take the height of 5,000 and you try to infer about the height of the rest of the Thai people. Well, in time series, it would be something like you have 5,000 days in the past of the gas price, and you try to say what's going to happen to the gas price from today tomorrow onward. Okay, so that's the sense of sample. Okay. Now, but here's the thing: when I take a sample, I really don't care about that sample. I only care about what it allows me to infer about the rest. So when I look at time history of oil price or gasoline price, I'm not looking at it from a historical perspective, like I want to know what the history is. I only care about history if, and that's a big if, it tells me something about what the future is going to be like. Okay? So the value of that sample is strictly, and I have to say this 1,000 times, strictly its inference value. Okay? So the general population, general phenomenon that you want to analyze. In this case, you want to sort of like quote unquote predict. Yeah, I will use the word predict loosely for now because we'll formalize that later. So by definition, again, data is always about a sample, a subset of something, subset of events, subset of phenomena, subset of entities. You take a measurement, you take a record, but that allows you to create a model that will infer something about the rest that you haven't seen. Okay? Which means the data in itself means nothing unless you can do analysis. Okay? And this is something that perhaps I don't need to say today, but maybe 10 years ago, I would have had to say a lot. Just because you've got the data gets you nothing. You have no insight from it. Okay? It's the data multiplied by the mathematics that gives you the insight. Okay? So I'm glad I think in the modern world, people are more conscious of that. Missing half thing. You can't do anything with this data. Data is just there. It's like raw beef. Raw beef you can eat. Raw pork. You cannot eat raw pork. Okay? And I eat raw pork. You have to cook it. Right. Now, let's think about the format it comes in. Now, here's where you have the old world and the new world. The old world is what's called tabular data. That means, think of Excel. That's a perfect visualization in your mind of what a tabular data is. Again, data is the measurement, right? About the sample. Well, how many samples have you got? 5,000. Well, that goes down row 1, 2, 3, 4, 5, 6, all the way to 5,000. And what do you record? Well, you put on the column, right? So think of Excel. That's a tabular data. Okay? It's a table, right? Every single item refers to different samples or different items. Each of them has measurement on the same dimension, right? That's why if you say, I'm going to record the height, it's always going to be like centimeters. I can't record centimeters for one guy and meters or inches in the other. Okay? It has to be congruent. That is congruent. Okay, so that's basically what a tabular data is. And that is the form of data has been in development from human history, again, since the Sumerian up to the 70s. Yeah. And it makes sense. The very process of recording is also done on a table, right? So you actually, when you go and collect data, you have like a sort of a piece of paper that's the table, and you record that. And when you put that in Excel, it looks exactly the same way, same thing, right? So that's what we're talking about. Now, today, this class will go to other form of data that doesn't come in that shape. Okay, but I'm not going to go to that yet. I'm going to say, well, first of all, let's talk about this. Okay. There are actually, now this is something I'm going to say that is going to sound very simple. It's like I'm insulting your intelligence, but surprisingly, not surprisingly, but I can tell you this, professional data scientists make logical error, inferential error, because they are not conscious of the choice of numerical scale they work with. So today I'm going to talk to you about what is called number scale. It's something simple, it's baby, right? You can teach this to a fifth grader, but if you're not conscious of it, you will actually make the wrong inference when you're a professional data scientist. Kind of funny. Yeah. So first, well, the data, what do you record, right? You can think of, let's go by two groups first. One group is sort of like descriptive or categorical, you know, like blue, like, you know, beautiful, yeah, soft, that sort of thing. And then you can have something that is quantitative or numerical. You actually put a number to it. Okay, 7, 8, 33.2. Okay. Now, those that comes in the categorical or descriptive, in terms of the number scale, that's what I'm talking about now, number scale, it comes in two flavors. One is called nominal scale. Okay. In other words, think of a computer. Computer doesn't understand blue. Computer doesn't understand pretty. Computer only understand numbers. Yeah. Yeah, this is up to the 70s, right? So computers only understand numbers like that. Okay? They don't understand blue, they don't understand pretty or ugly, they only understand 1, 2, 3, 4, 5. Well, same here. Computer doesn't understand Emily or Maya, right? Or Martin. But you have an ID. You have an ID. You have an ID. Computer understands that. So that scale we call nominal scale. It's a name. It's a name. Now, mathematically, this is very important. Mathematically, this is this thing here. You are only allowed to do one operation. Okay? That is checking for it. So I can say if Emily is the same as Maya or Maya is the same as Martin. No. How do I do that? Because your ID and your ID do not match. So it's an inequality sign. It's a Boolean logic. Okay, equality, inequality. That's all you can do. Can I say that, Martin, because your student ID is higher than Maya, that you're a better student? No, right? So absolutely no comparison. Same, not same. That's all I can say. Okay. Second, higher level of information is ordinal. Greater than or less than. Now I can do this. I can do something like, I give you a 1, I give you a 2. 1 is better than 2. How do I do that? Well, at the end of the year, I give a grade. So A is better than B. Right? Same thing as beauty pageant. You can say the winner is the most beautiful, and the second runner-up is the first runner-up is the second most beautiful, and the first runner-up is the third most beautiful. Okay? So you can say that who greater than, equal to, less than, equal to. But can I say this? How much more beautiful is Miss Universe to the first runner-up compared to the distance in beauty between the first runner-up and second runner-up? Can I quantify that? No, right? So I cannot take Right? So you have a number, and that gets you to something called interval scaling, where you have a measure of distance. And you have a measure of distance. So, what kind of things have a distance? Well, temperature, you need that right? You say, 27 degrees is 2 degrees higher than 25. 25 is 2 degrees higher than 23. I can numerically subtract. So what I can do is add and subtract. Temperature. Finally,
The interval scale would also be with the universe, if they did like the rating with the numbers, like the number 10 and then like a jury rating, and that's getting added together, and you will also scale, right?
that's okay. The information is 1 is better than 2, 2 is better than 3. Yeah. But before I get to the rating, I may have some quantitative scoring. So for example, perfect case would be this. Your grades would be ordinal scale. A is better than B. However, behind the scene, I can say, no, you're a good student, I give you A. You're not so good, I give you B. But if I did that, nobody would be happy. So maybe there's an internal criteria. So what I do is I give you an exam, right? I count your attendance, I count your project quality, and I get a score. And I make a cutoff. Something beyond 93 is an A. Below 93 is a B. But those are two different scales, right? If I give you an A and B grade, you still have just that, just A and B. You can only say that you are better than B, but you cannot say how much better you are because you don't have that access to that behind the scenes, right? So it's actually you map one scale to the other. But if I give this number, that's all you've got. Okay? I can tell you, I hope you don't mind. I like to tell 5 stories because I've got lots of experience. One of the things that happens in real life is this. You know what a credit rating is? Well, credit rating is a little bit like I do all kinds of exercise. This company has been borrowing with this leverage ratio, this and that, and historical, blah, 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 blah. And I give it a double A rating. The other guy gives A rating. And that's supposed to be it. But you know what? People don't do that. People do more than they should do. They try to go back and say, if there's some kind of numerical foundation to those numbers, maybe we can work backwards from the credit rating to the numbers. And they actually map this back. For example, if you're AAA, you have probability default of 0.4123%. Double A corresponds to 0.3 or 0.4 or higher. And they become religious about it. And after the crisis, the people realize they shouldn't be doing that. So yeah, again, it's not just professional data scientists who are committing error. So you can always go from here to here. But going the other way is very hard to do. Yeah. So this is what I meant earlier by saying that a lot of times data scientists make stupid error because a computer will always give you a number. Right? My machine learning algorithm will give you a number. It's up to you to understand that based on how you built it. You can only say 1.3 is bigger than 0.9, but not 5.4. Okay, that's the conscious thing that I want you to be aware of. That's the pitfall. The computer gives you 1.3 and 0.9. But you understand from the way you built it, it's only a relative, it's only an ordinal scale. 1.3 is better than 0.9. If you did something else, like saying it's bigger than 0.4, you're wrong. You actually inducing more information than is warranted. Okay? And data scientists do that all the time. In fact, I'm saying this in the professional data science. And that's why it's called, in Thai, it's called Yapa. Means grass just in front of the den. Okay, it's a very easy thing. Okay? But you just walk over because it's the first piece of grass, right? You cow and open the den, You go run off in the field, and you've got this piece of ground that's in front. That's the EC that you think together. So I wouldn't spend so much time on this if I didn't think it's so damaging in real life. Okay. So rank again, this is very important. So this is thinking about tabular data. So when you put in black, blue, yellow, green, Excel records that. Numerically, it just knows that it's a different ID. Right? Black, blue, green, you put that in ASCII, it's a number. So you can say inequality, you compare, you can add and subtract, and finally, the last thing is the ratio when you have absolute zero. Because like temperature, you don't have absolute zero. So you can't say, can I say that 50 degrees is twice as warm as 25 degrees? Can I say that? I can subtract 50 and 25 get 25. But if I divide 50 by 25, I'm wrong. 5? Because 50 divided by 25 is 2, right? But if I did this in Fahrenheit, I'm not going to get 2. Because it's a different zero. It's a different zero. Okay? So you can't do that. Yeah. So you can't multiply, you can't divide. But if you have something like absolute length, yes, there's the notion of zero. Maybe there's even the notion of negative. Right? So this is very much something that I hope has been drilled to you. And if not, I'm doing it again today. I don't consider it a waste of time. I think it's very important. But this is something that even from statistical class, probability and statistics, they should actually drill this into your head. Okay. For example, when you choose a probability distribution, you have to know what can you do here. Okay. Now, today, we are going to deal with other kind of data. Again, we focus on data as recording as a measurement. So if I record your voice, I can't put it down in an Excel. Can I put your voice in Excel? No, I can't, right? Right? But if I record your voice and I use it later to check whether or not you are the same person you claim to be, okay? Or I have an app, take your voice, and based on your voice, I try to analyze how old you are. Okay? So the essence is not whether or not you can put on a piece of paper or you can record it. The essence is that it gives you something. Now, in this case, I told you that normally when you study sample, you can interested in something else, right? Well, in this case, I'm not interested in another person, but I'm interested in another aspect of the same person. Your voice belongs to you. I take your voice and make analysis. I infer another dimension, which is your age.
So I would argue that you can put the voice in Excel. Like you can do a T.
Yeah, yes.
And then over time you have the frequency.
That's strictly speaking not true. Strictly speaking not true because okay, FFT is true to the sense that it's probably if I make an FFT map of your voice and I regenerate it back, human ears can't tell the difference. But it's still technically a numerical approximation thereof.
I mean, yeah, but if you do it with the appropriate like the frequency, then it's fine.
Okay, then in that case, I'll tell you what the difference. The difference is that this thing is one number. Right. Okay, you can never do this with one number. Now, one number you can make it into a vector. Okay, so technically it's a scalar.
Yeah.
So if I want to be precise about it, I say that the data we've been working with up to the 70s is the tabular data of scalar. So each cell, you this dimension, one number. You, another dimension, another number. Another person, okay? So each little cell input one number, scalar. Okay, scale, and that scalar comes from the word scale. Right. So that brings to my admission today. Why did I say that this class is not really about big data? Because I'm only dealing with one aspect of data. Two, but not. We'll talk about what big data is. Okay. So you can think of big data as what to do when you can't record a scale. You have to record a vector. You have to record parameters. Okay. So if I say I do a Fourier decomposition of something and I keep just the 20 phase frequency, and I keep a 20. Okay. So population. Okay. And this is a modern distinction. This is what I was talking about earlier. In the old days, you only get data you record. Okay. And in fact, I don't know if you know this, but in the old days, I used to work at the Bank of Thailand. Bank of Thailand is very good with data. They start, Bank of Thailand is 150 years old. So in the beginning, they would write everything on pieces of paper, ledger, right? So as we transition to higher technology, there'll be one interim period where you still gather data by hand. And then you take this pieces of paper or ledger to a human person who keeps that in his computer. So the number will go into paper medium first. And then you have like 100 of fairly underpaid stuff here. Okay? But it's still recorded. Even though it ends up being digitized, it's literally recorded. And you can imagine that, well, you have to invest time and effort to record. Otherwise, you throw it away. Yeah. So you get to this generation where everything you do is already pre-recorded. What do I mean by that? Because you're carrying a telephone, your telephone has a GPS, it's already recorded your position. Right? You don't have to write it down. Okay? So there's a big difference between me in the old days. I said today I went to here and I went there and I went there and I recorded. And that's my journal. Nowadays, wherever I go, the information is there. It's whether or not I choose to keep it. Okay? If I don't choose to keep it, it's in the cloud somewhere until whatever Google decides to use it or not use it. Okay, if they decide to use it, it's there. Okay? So it becomes a storage cost. It's not about recording cost. It costs nothing to record. It costs something to keep it in a file. Okay, let's keep that and cloud database. So that's where we are. Now, let's talk about big data. Big data, wherever you hear that term, it's always talked about in two thematic settings. Okay, one is to talk about it in terms of of phenomenon, opportunity. In other words, with this big data, you can boost your intimate knowledge of your client and blah 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 and this that. Yeah, and that's sort of like the sell side, the demand side of what you can do with that big data. And then there's the shore. The shore is like, well, if you aspire to do big data, okay, you don't have to have a lot of paper and pen, but you do have to have something. And that's the infrastructure, that's the technological aspect. Now, let me expand that. Okay. Now, this is where I'm going to focus on the big data. In this aspect, there are three definitions to what makes big data. Remember, you used to have tablet data. It costs something to enter. It costs you a human being to create and blah blah blah. So you don't have a lot of. If you have an automated process of generating data, and you have a platform for harvesting, then you can imagine that you can speed up the efficiency of the storage. So two things that can happen. Every time you talk about efficiency, it's always the volume and speed. Right? How much? How fast? Yeah.
What about quality?
That's coming later. But the first D is velocity. Now, this velocity means normally it means ingestion rate. What it means is the rate in which the data is created. Yeah. Yeah, you used to walk, but your walking did not result in data. So you didn't generate data. But if you walk and generate data as you walk, you can almost imagine that you generate data every second. And if you have 10,000 people with an iPhone or whatever, you have 10,000 per second. And let's say assuming 1 second is 10,000. So that's the velocity. The flip side of that is that as the velocity come in, you have to handle it quickly. And if there's some kind of processing, you have to give your response back equally quickly. Because we now, I'm so you get those spoiled to use this, right? So if you go to a chat bot and ask about something, we don't expect it to come back tomorrow. We expect it to come back right away. And that speed costs money. That speed costs money. So that's the opportunity set. And volume again. So all this velocity and volume, this comes with the high efficiency. Right? Now, this is what I mean by this class is not a proper big data analytics. Because we don't deal with the velocity and the volume. The reason we don't deal with the velocity and the volume is because this aspect, the technology you need, like Spark, data, it's not something that you learn within the classroom environment. Okay? And even if, let's say for some reason, last I just went crazy and bought Spark server so that you can train on this. When you go to, so first of all, not all of you will go to big organizations that will actually have for on-prem Spark server. Sometimes you would just pay Google to do it. So useless right there. Second of all, if you actually go to a big organization that has its own Spark server, their system will be quite specialized. Then you have to retrain anyway. So there's almost no educational value. Remember, the objective of this class is to put you in the mind of a driving seat of a data professional or data scientist. Well, that is one feeling you're not going to get from this class. You know, how to program huge Hadoop distributed database and play with it to do search query. So that's one thing that's not in there. So when I say this class is big data analytics, this aspect of big data is not covered. Okay. But what is covered is this thing, variety. So they always say that big data has 3D, volume, velocity. We don't cover that. Yeah, so that's from the rest of the class, we're not going to mention that. Although, if you're interested in that, I can point you to training. But we're going to deal with that. Okay, we're going to deal with variety. So, variety. Well, what do I mean by variety? There are actually 4 specializations. Think of it as, if you're a professional, you have to have a very good experience with this kind of data. Professionals sort of like come in 4 varieties. Okay? One, the variety refers to multimedia. We talk about the sound, right? So basically, it's captured in digital form. It already is kept in digital form. And then that digital form does not translate into a simple scale. It can be voice, it can be video, it can be picture, it can be anything. So this is the multimedia world. Okay, this is the big data that most people are familiar with because we play like. The second group of big data has to do with this kind of what I call geographical coordinates. But I don't mean just geographical, but like iPhone. Everything, from geosensor, from probing into the mantle layer of the earth or trying to do oil and gas exploration. So any kind of spatial temporal data. Okay? Where the information is spatially and temporally indexed. Okay? So traffic data, for example, there's a example of this. Yeah, the flow of data, right? You can say you turn on the tap and this tap 5 liters per minute flow of water. Well, you can do same thing with cars. You can say this is 100 car per minute traffic. This is a 50 car per minute. This is a 2 car per minute. And that has your spatial index to it. Okay. Now, the other one, the variety is called network protocol. So these are really data that has to do with like internet traffic proper. And this will be professionals that deal with a lot of time with internet security, right? That sort of thing. So this is also a very specialist area. And finally, there's this final thing, which is Internet of Things. Now, this Internet of Things in Basai program will be covered more or less in the Internet of Things class or robotics class. What it means is, this is really the reason why we generate it. Internet of Things means that everything has a everything has an access to digital domain. So if this thing, there's actually a microchip somewhere in there that does. Okay, so if this thing actually links to some kind of Bluetooth to your phone, okay, and you can set temperature control, okay, or it can just report to you. Okay? Now, obviously, nobody wants to know how long this will is, but if I have a big field of green, cotton, whatever, right? I certainly would like to know the soil temperature, 500 yards without walking there and sticking my finger. Yeah, so I have a high quality moisture sensor. You can have sensor that measures nitrogen content, all kinds of stuff. Stick it in there with some battery, maybe with a nice solar panel, keep the battery going. And then just ask it every hour and the information you need. Then I have a map of all the temperature, the heat, the humidity, the nitrogen, and all kinds of stuff. Okay. Now, Internet of Things just means that all these things is not just in the old days you have this communication as well. Radio wave and stuff. But now it's in digitized form. And so when we say Internet of Things, we mean the modern world where all the information that is in digital form. Okay? It's not just a radio wave, it's not just a sound. So in the old days, you would have something like a microphone next to a harbor that listens to the waves and they transmit them. So when we talk about Internet of Things, that means this is already digitized. It's not analog, it's technology. So that's the variety. Now, we are not going to deal with this. We're not going to deal with this, but we probably will deal with a lot of this image. Okay. Having said that, and this is where you guys know Pareto principle. Yeah. Like 80% of things that matters is accounted for by 20% of things that we do. Right? Well, same thing happens here. This is all very sexy to study, but chances are in your business, 80% of what you need to do would just be analyzing. Okay, so it's not as sexy as analyzing human voice, It's not as sexy as analyzing data either, although people study some of that. Okay, but meat and potato, you know what I'm saying? Okay, so Pareto principle is the meat and potato of what you do. You need to really be able to understand numerical data. You need to be able to understand numerical data that represent nominal, ordinal, interval, and ratio scale. Okay, and do something with it. Okay. So that's what we mean by data. Do you guys need to take a break or anything? I can keep going. Okay, I'll just keep going. Right. So let's talk about analysis. I'm going to say categorically right now. Analysis is building a model. Okay. Some of you may have the impression that you can do analysis without a model. That's because you have a very narrow definition of what a model is. You think a model is a mathematical equation, so it's a model. If you don't derive a mathematical equation, you don't have a model. If you're just looking at the plot, it's analysis without a model. No, I'm going the other way around. I'm saying everything is building a model. Yeah. In fact, a model is the middle step of every time you have a mental process that say, if, then. Okay? If I observe this input, then I expect that output. The connection from if to then is always on. Okay? Now, the simplest kind of model is not, you would say it's not a model at all. It's just saying in the past, right? In the past, or like some kind of lookup table. Okay, so you press this button, and that color should light up. If I press this button, that color should light up. So it's like a lookup, right? So that lookup is the model. It's not a sophisticated model, but it is a model. If this button is pressed, I expect red light. If this button is pressed, I expect blue light. Whatever. Okay? It could be simple, but it is a model. So everything you do is model building. So that requires me to go on. By the way, I made this because I have the pre-course for the incoming question. And you can imagine that building a model is what makes us as a species more successful. Okay? People say, you know, why are human beings more successful than other hominids or other primates? Because we have language. Well, what do we use language for? Right? We use language to coordinate. But how are we going to coordinate if what's the objective of coordinate? I coordinate my action only because I have some kind of anticipation. I can coordinate my people, my friends, to stand here below this ledge because I have a model that if I spook the mammoth is going to run with me. That's the model. And that's the model. Then I can coordinate my friends. If you take your big rock, I take my big rock, and we go hide behind it, and smash the mammoth. Okay? So model, in a way, is what gives competitive edge at all levels. Okay? Because we don't operate in the past, we live in the present, we take information from the past, we analyze, and then we make some kind of prediction of it. Okay? So it's model building. Now, technically, I would just give you that there are actually three kinds of models. And the first, and this is from operations research. I don't know if you're familiar with that. Any of you British? Okay. You owe your independence to operations research. That's what 1 year that of it. Very good. Operations research makes a stylized categorization of modeling. One is to model like a representation. So I told you the model is in out, right? What in out does is that it mimics the real system. Okay? So what's the real system? I yank the horse by the tail and it kicks me. That's a real system, right? So if I build a mathematical model that says I yank the tail and the animal kicks, that replicates the input-output response. Right? So it's a toy. It's a toy. It looks like a real thing, but it's not like a stuffed horse. You can have a beautiful stuffed horse that looks like horse, but it's not a model because when you put the tail, it doesn't kick, right? But if I have a lookup table that says if tail equal to pull, leg equal to kick, right? It doesn't look like a horse. It's actually a piece of computer code. That is actually more realistic from a modeling standpoint than the beautiful stuff. So that's what a model is. Now, why would you want to do that? Well, because you want to try a few things. You want to try to pull the horse, simply cut it, but you don't want to do it with the real thing. Good example would be a traffic model. So if you have a good traffic model, I can find different green light, red light algorithm. And people do this, by the way. This is real. I'm not just making this up. I can have an algorithm that says, let's maximize the number of congruence. In other words, green followed by green, followed by green, followed by green, all the way down. Or I can just make it random, or I can say, if this green is red, then green is red. And I can try this with the computer model of traffic. Now, I can do this 1,000 configurations overnight. Can you imagine finding in real time, right? People will get really mad. So, why do you have a model? Because it's cheaper, it's friendlier, it's practical to manipulate the model than it is to do trial and error. Okay, so a model in that sense is a tool. Okay, this optimization model. This starts system model. Basically, it just looks at input output as long as. Oops. Maybe that's a little bit too big. Where are we? Yeah. I'm going to spend a bit more time on it because this kind of model building is very much what we're going to spend time on. But tell you what, before I go there, let's collapse this and talk about this too. Okay. Now come back. So a system model is basically building y is equal to f of x. Okay. And hopefully it's realistic in the sense that if I give the same x to the real system, I get the same y as my model. Okay. The second kind of model is called optimization. This is like I already know the input output. I already know the input output. But some outputs are better than the other. Or some patterns of outputs are better than the other. So maybe I don't want a particular pattern. I don't want a particular output. I want some kind of statistical property of output, like doesn't vary very much. For example, you don't want your input output to be a pacemaker. You want the heart to be right, nice 70 beats per minute. It can be 80 beats per minute, but as long as it doesn't fluctuate. So that would be so. There's some kind of criteria. So it's not if X then Y, but it's sort of like, what if I like the Y to be in this way? How would I choose the X? Right? This is called optimization. And finally, there's a optimal control problem this sort of like, it's more dynamic. I think this is not relevant to most of us here. It's sort of like, you don't really want it to be good or bad, but you want it to be sustainable. And that's actually very tricky. For example, I give you an example. Yeah, I started my career with the Bank of Thailand, my scholarship, Ph.D. The Bank of Thailand doesn't want to maximize inflation. Yeah. Bank of Thailand doesn't like inflation, but Bank of Thailand doesn't want to eliminate inflation. So the criteria is not make inflation as low as possible. No. That would be like, how do I choose X to lower the Y? Y is inflation. Bank of Thailand said, nah, it's okay. As long as it's within certain band and it doesn't get out of control. So it doesn't have that direct desire, but it's sort of like gently handling, keeping things in check. Yeah. And this is very much in engineering spirit. A lot of engineering problem is not about to get the most efficiency, and that would be optimization. A lot of time is like making sure the system doesn't blow up. And that used to mean a lot when, in the old days when things blow up, so steam engine blows up, the boiler room blows up. So you don't want to get the boiler room to be operating at maximum efficiency. You just want to make sure that the boiler room is ship, operate decent level of efficiency, but doesn't blow up somewhere mid-night. Okay. Now, so this optimization model, I'm just going to mention quickly. I'm not going to expand on it, but in a way, it's a little bit like inversion. If X then Y, and you ask the question, what if I want Y this way? What X would I get? Should I do it? Yeah, it's a little bit like inversion, not quite. Anyway, so that happens a lot in calculus and blah, blah, blah. But I'm not going to spend too much time on it because most of the data analytics is about this. It's about this core meat and potato. So what are we trying to achieve? We're trying to gain information advantage by building the model. Again, to build a better model, we can hunt woolly mammoth, survive. So there are two. So imagine I write an equation here. Yeah. Now, so far I've been saying that I want to build this F. Build this F. Okay. To be realistic. Right? Be realistic. Whenever I get this X, I should get the right Y. The right prediction. So the language is if I get this X, I get that Y. So what about relevance? What if I build a perfect model of X and Y? X would be something like humidity, right? And Y would be chance of rainfall. Okay? But my model only operates at temperature close to the surface of the sun. In other words, my X is completely irrelevant. That's not good, right? That's not good. So there has to be another aspect of modeling that focuses on the distribution. So this is if X, then Y. But which X is likely? Which X is not likely? So you can think of, and this is, Basai is all about integrated education, integrated innovation. All the tools are mixed. Hybrid, mathematics, statistics, computation. But if I were to be able to say one sentence that sort of like separate math and stat neatly, this would be that one time. Statistics tells you what X you expect to see. Mathematics tells you how to get Y. Yeah, that's it. That's all I'm going to say. So that's a nice clean separation of math and statistics that I can make. But that's not going to stay. Because, in the future, math becomes statistics, statistics with math, But if I was to say, a very nice, hey, you are a statistician, what do you like to do? I like to see, what X is like. I'm a mathematician, I build models, what I like to do? Well, I like to be able to tell you what Y is in X. Okay, it's that kind of distinction. So, the first question is, where are the X's? Where are the X's? Again, to make it relevant, if I make a temperature forecast model and it only works for X equal to 500 Fahrenheit, nobody's going to buy this weather forecast model because the input is completely irrelevant to life, right? So where are the X's? Well, so there are, and I'm saying roughly speaking, two kind of analysis that to do. One called distribution analysis, and that's the world of statistics. One is cluster analysis, and that's the world of machine learning. It's not hard to find, but roughly speaking. For example, so in this case, distribution analysis, mostly statistical analysis. Okay, this is when you study the distribution, right? This thing has normal distribution, student key distribution, okay? You look at the data, you make some kind of inference about where are the X's? If I see these X's in the part, what kind of X I should see with you? Yeah? X. Rarely does this involve machine learning. Okay? There are occasions, by the way, I just throw out the name just to get from the existence. Variation of autoencoders is a machine learning algorithm that actually outputs statistical information. Right. Now, there are special cases on this that I want to mention that has to do with what's called data mining. And this is kind of like, this is closest to, remember I said earlier that everything is a model, even though it doesn't look like a model, or data mining doesn't look like a model. Data mining looks like a lookup table. I can see a bunch of this, and then there's a bunch of this, that, this comes with that. It doesn't look like a model, it looks like a lookup table, but it is a model. So that group is called data mining. We actually probably cover one class just on this, on frequent identity, not because it's interesting, not because it's fun, but because it's the meat and potato of market analytics. Okay? Again, I have to do a little bit of fun. Okay? I have to say, I have 15 hours, I'm going to teach you everything I know. I don't hold back, but I have to choose. So my guess is, if you go into whatever, fintech, you go into innovation, at some point you are going to find yourself in a marketing analysis situation. Right? So this would be one of those things where, brute force market analysis. Using item set, sequential pattern, sort of like really just pure association. Every time you go to 7-Eleven, right? Well, you buy Coke, well, if you buy salty nuts, probably like to buy Coke. Okay. So whenever somebody clicks on that, it gets Coke, something like that. It's that simple. It's that simple. It's not sophisticated. But we'll devote time on it just because it's ubiquitous. Hopefully, maybe in 5 years' time, I might just drop it from the curriculum because it's so boring. Anyway, well, cluster analysis occasionally can be like statistical distribution, but most of the time it's using what's called machine learning. In particular, it's paradigm called unsupervised learning. Unsupervised learning. Now, with data mining, I told you, right? Simple association. Well, cluster analysis is a little bit like association,
but association of who tends to be around who. Yeah, who tends to be around who. So, if yeah, I line all of you up, yeah, and by height, yeah. So not order, but literally interval ratio scale. So I put down, 5 foot, 6 foot, and you have to stand where you are. So sometimes same height, let's stand the same spot. Let's say that based on that, in that line of height, I can see that there's a lot of short people and there's a lot of tall people. For some reason, it's not the bell curve. Could be. Right? So, and maybe I do some other dimension, male, female. Now let's be completely stereotypical. Chances are what you would see is a bunch of taller male and shorter female. Yeah, I'm not being naive. But you can see that in whatever dimension you start to introduce, there's a natural factor. And the reason why we use machine learning is because, look what, we want to do this in 11 dimensions. If I were to do this in 2 dimensions, I can do it by hand. In fact, you can do it with a plot. So clustering analysis essentially becomes machine learning job because you can't handle more than 2 dimensions. Humans can't do that. Okay. Then there's another problem. Well, I'll talk to you about it later. There's a trick in machine learning where you reduce higher dimension to 2 dimensions with the criteria that if you close in high dimension, you close in 2 dimensions. Okay, that's called dimensionality. We'll come to that. So, and that's what I mean by where are the x's? Where are the x's? In school, okay? And the reason for having supervised learning is because just based on this closeness alone, you don't have to say anything. You say who comes to whom. Yeah, it's called unsupervised. I'll tell you why, because you have to understand what supervised learning is to understand why this is called unsupervised learning. So anyway, let's go to the next one. And this is another huge part of what you do. Again, keep going back and forth. Data is only useful to you because it allows you to have insight into something, allows you to predict. Data is your resource to produce insight. Insight comes in the form of models. Models that we're talking about here are basically system models that represent reality. And what represent reality? Well, what's the typical temperature of a given day? So that's where our x is. If today is that temperature, what's likely to be the temperature of tomorrow? That's x to y. Okay, so those are the 2 kind of models you want, right? What kind of x do I get to see? Do I expect? And for whatever value of x, what kind of y do I get? So let's talk about it. If I knew x, what can I say about y? Okay. Now, y here then separates also. Remember that the scale I noticed that the number scale, there's qualitative, right? That goes into the nominal and ordinal scale. And then there's quantitative that goes into the ratio and interval scale. Well, if you use those 2 aspects to categorize y, then you can also have y that is qualitative. Okay? Qualitative. For example, input x. X is a picture. Y is a quality called cat light. Y is quality called dog light. What you get? You get a model that recognizes cats and dogs in pictures. So, those fall under things called classification. On the other hand, if the Y tends to be quantitative in nature, yeah, interval scale, nominal scale, like tomorrow's temperature, it's usually called regression analysis. Both of which are terrible terms. Both of which are terrible terms. I'll tell you why. But it stinks. It stinks. It stinks because regression analysis does this sort of thing. Give me a bunch of ways, X and Y, and I'll give you a relationship. And Y is numerical. Classification analysis is also give me a bunch of X and Y, bunch of pictures, X or not, picture, X or not, picture, X or not. And I'll give you this model. But it's quantitative. But it's it really is a bit of a cycle. Regression needs something else. It comes from Sir Francis Galton, a British mathematician, scientist. So they're like, you know, what people's offspring regress to their parents' house. There's some kind of a go back to. Okay, well, we don't mean go back to anymore. We just mean anytime I can make Y out of an X. That's a regression. Classification is also a factor. You know why? You guys have friends? I mean, you guys have friends in biology. In biology, classification means the science of creating classes. That's like, I see this animal, I name this dog. I see this group of animals, I name this cat. That's classification. If I pick up another animal, I look at it and say, hey, this looks like a dog. That's identification, not classification problem. Okay, but in our world, that's called classification problem. Okay, so in our world, classification is identifying to pre-created classification. Okay, so you make sure that when you talk to your biology friend, you're not talking about the same thing. Yeah. Right? So classification means I organize things into class. Identification means I take something and I say, where does it belong? Well, in our world, that's called classification. That's it, but you figure it. Yes, you make it. Okay. So when regression analysis, usually you have statistical method. Why? Again, because the Francis Galton has already created a regression analysis model for us, but more and more is machine learning. But it's the machine learning of the type called supervised learning. Now, why is it the difference between supervised learning? Unsupervised learning, because you're focusing on the X, you're free to organize X however you like. In a way, it's like proper classification, clustering analysis. But with this, what you do is you have X, right? One guy, X number one, equals to Y1, equals to X2, Y2. And you have a whole bunch of them, right? So your model is to replicate this. So if I give you this X, I should give you that Y. If I get something else that's different, the programmer should tell the computer wrong. If I get something that is both, computer should say right. That's what I mean by supervision. It's a little bit like when you were a kid. You say apple, and you pick up an apple, and your mom says good, right? And when you pick your poo-poo and you say apple, your mom says bad, right? It's supervised in that sense. There is an answer. There's a right, wrong. The object, the nature of the computer is to be able to make the right prediction versus wrong prediction. Okay? But unsupervised learning is also like when you were a baby. When you associate arrival of your mom with warm milk and cool stomach, right? When you associate barking dog with something scary and, you know, chaos, whatever, right? This is sort of like association clustering. So you cluster your mind with happy feeling, with fat and so forth. Okay? So that's unsupervised learning. By the way, those are the two machine learning paradigms. There's another paradigm, by the way, that on top of this called reinforcement learning. I might as well give you a sentence on it. In machine learning, we'll obviously go into specific model. There are three modes or three paradigms of learning, very much like an infant, young student. Young infants learn by unsupervised learning first. Okay, just maybe can't relate in language. So it's not talking, just associating mom with being fed, whatever. Okay, unsupervised. Supervised learning is when your mom and dad start teaching you apple, dog, blah blah blah. Yes, wrong. Okay, so there's immediate right and wrong. Now, over time, you also learn to pick up behavior. Right? Like if you snitch on your siblings, if your siblings don't like you or something like that, or if you always like come and take toys away from your friend. So nobody, if your parents is there and say, Johnny, don't take toys away from your friend, that's supervised learning. You need it direct, right or wrong. But if you pick up over time, you know, I keep taking people's toys, and sooner or later nobody likes it. On the other hand, if I bring toys, okay, nobody tells me this is the right action, but I notice that, you know, I bring my toy and share with my friend, I bring apple and share with my friend, pretty soon everybody likes it. Right? This is kind of reinforcement behavior. That's called reinforcement learning. Machine learning computer can do that. Okay? So there's a learning that happens just a little bit like statistics, where things without being told. There are learning like if this X it should be that Y. You give me something like this, no, it should be here. If you give me this, yes. And also there's kind of an input output over time.
So usually babies to learn like walking by observing, trying things out for themselves.
I would
Does that go
imagine.
to unsupervised or
I would imagine if I were to categorize, if I were forced to categorize, learning through walk is reinforcement. Because when you learn, you build a memory of how you react to your sense of balance, right? Your parents is not saying that if you feel like this and you do this, you're gonna fall. That boy, that girl. If you feel you're falling to the right, you should pull to the left. Nobody's doing that. Nobody's doing that, right? Now, on the other hand, there's definitely a reward. Because if I did this and I fall, I hurt myself. If I did this and pull myself back, I don't hurt myself. It reinforces the sense of balance, right? So this kind of long-term reward for doing the right thing. Not giving the right answer, but doing the right thing in response to the environment. That would fall under responsibility.
why is it not unsupervised?
Why it's not unsupervised learning? Because in unsupervised learning, it's like a free association. There's no objective there. There's no payoff. There's no payoff. Okay, so you can think of it as like unsupervised learning is a human being with cognitive power to organize things. We naturally want to organize things, so we group things into class. Nobody's telling us to do that. There's no payout, but we do that. We do that. That's why we stereotype. Okay, stereotype is unsupervised learning. Nobody told you to be, well, some parents tell them to be racist, but you know, sometimes you stereotype. You don't need to be racist, but you just make free association. Okay, because of the movie you see, maybe the movie is made by racists. I don't care. The point is, nobody told you to do that. To make an association, you form that automatically. With reinforcement learning, there is a payout. It's just not immediate. It's not bad. This is Apple. Bad. Okay. Not take your friend's toy. No. You can take your friend's toy. But after 10 days, nobody likes you anymore. it's not immediate feedback. It's reinforcing good behavior over time. So it's almost like your brain has statistical machine that keep tabulating. Hey, you know what? If I share my apple, share my toy, people like me. That's what it is. Okay, but look, but your parent is not there at the kindergarten, helicopter and parents say, Johnny, share your toys. No, that's immediate, that's supervised. Now, why it matters is because this is the algorithm that human beings learn. And because of that, computer scientists model machine learning algorithms after that. Okay? There's other kind of learning as well, adversarial learning and all kind of stuff. But the three major paradigms that. Now, remember I told you that the analysis at the model is like a system model, optimization model, and optimal control. Reinforcement learning is very important. You can imagine that just like a baby learns how to balance, right? So that doesn't fall. The Bank of Thailand also wants the Thai economy to balance, grow, but doesn't have to go double digits as long as it's steady growth, sustainable growth, right? So some of these things kind of dovetail into each other very nicely. So reinforcement learning and optimal control problems, like marriage, maybe, okay? For system model, basically it's unsupervised and supervised learning. And for optimization model, sometimes you don't even use machine learning, you use mathematics, optimization or inversion. Okay. So if I were to, nothing hard and fast. Nothing hard and fast, but system model. This is also model inversion, but in a generic sense. In optimization sense, you don't want to invert any X for any Y. You want to invert the best X for the best Y. Okay, so I'm not going to expand on these two guys. Okay. Now, in terms of statistical method, well, again, where are the X's? That's one problem. Give me, if I get X, what is the Y I expect to see? Well, both of these statements can be stated probabilistically. Statistical method always produce results in terms of probability. Yeah, sometimes not quite, but ultimately it's high probability. So if you talk about where are the X's, it's the probability of seeing X between here and there. What about X and Y? Well, give me X. I have a high probability of seeing Y here. Higher than many variables. So it's still probability. So even though you give me X, I give you Y, technically I'm still talking in probability terms. I don't give you Y, I give you Y that I believe most likely. There's still probability. So at some point, statistical method is based on that. Now, you know the difference between probability and statistics, right? Probability is the mathematics that describes the likelihood. Statistics is to choose that mathematical expectation from data. Okay? So mathematician can dream up probability function however they like. They just think of some function that adds up to 1. Because probability adds up to 100%, right? And you cannot have negative probability. So if I create a function that is non-negative and add up all the possibility adds up to 1, I've got myself a probability function. So that's mathematics. Now, whether or not this is something I dream up just for fun, or real life data looks like that, that's it. So, what do statisticians do? And this is very important because this is what analysts do. Statisticians walk into a job with a toolbox. Analyst. Okay? In fact, that's what you are. You go to a job with a toolbox. Okay? Put it down. Take the problem and you match what's in your toolbox. And that's always your job. I don't care if you're a plumber, I don't care if you're a statistician, a physicist, a doctor. Okay, you carry a tool bag. You go see your patient. You go see a broken pipe. You go see your whatever. Okay, you go to your problem with your tool bag. Well, the tool bag that statisticians do have is a whole bunch of probability numbers. Yeah. So maybe I'm a, you are a student, you're a novice statistician, you know 5 probability. I'm a professional statistician, I know 50 distribution. Okay, so I can actually choose one that's really good. That's it. Now, what's the patient? The patient is the patient. Well, it's that kind of thing as well. Data analysts do that. Except the tool is not necessarily probability tool. But that's why we're going to spend a lot of time here. Okay? But the model actually is very similar, right? Very similar. If the problem involves some kind of number, and you want to know where X and R, and if you know what X are, you want to be able to tell what Y are, what Y is corresponding to that X. That's your job. That's your job. So this can do that. Yeah. The difference between statistician and machine learning specialist is in technique. And these techniques are limited to probability language and limited to probability that mathematicians over the past 500 years have devised. There are actually maybe 300 probability distribution out there. Yeah. I always tell my students this. If you know 10 probability distribution really well, you're not making anything. Unless you work in a very specialized job, in which case, yeah, for example, if you know normal distribution, students P, exponential, gamma, beta, you can work in a financial profession, binomial, okay? But on the off chance that you apply for a job in insurance, and not only life insurance, but catastrophe insurance, you might have to pick up a few more esoteric distributions. You know, like Gradle, EV, all kinds of, but they'll tell you. What I say is that unless you go into those specialist areas, you only need to know 10 distributions in life. Maybe even 5. Okay? In terms of actual use. Yeah. So we can talk about that, but